I'm going to talk about the learning-aided neural optimization with imperfect state prediction. As Srinivas was saying, these are my code collaborators. So I will not repeat their names. Right. Okay, so let me start with a very simple example to motivate the problem, and so that you sort of see why we're doing this and what problems we're interested in. So imagine that you're operating a ride-sharing platform. So your job is to match customers to cars. Okay, and also let's say that you divide the customers into different classes, and also for here we're doing it for female customers, male customer, and the other type is business customers. And you also group the cars according to their preferences. And so the female customers will prefer cars like this, and so on and so forth. Okay. Now, let's say that in time one, you get this set of customers and you get this set of cars. So what you're trying to do is let's try to assign them to cars. And so you match this female customer to this red car. You match this male customer to this green car. But then we don't have any business car for the business customer. So what we can do is that we're going to assign him to this orange car here. So he might not be very happy, but we'll just do it that way, okay? Now, and then let's say that in time slot 2, we get a different set of customers, and we get the different cost status. Now we will do the matching again. So we match this female customer to this red car. We match the male customer to a green car. Now we have this business style car, but then the business user is already gone. So what we do is that we assign the female customer to this business car. Okay. Now, as you can sort of see from this example, if we knew that the business car is coming in the next time slot, we could have asked the business user to wait for a little bit, and then we can make him happier. Of course, this relies on what prediction we have. But you can sort of see here that this is the idea. Okay. Now, people have looked at systems like this, and here are the questions that we usually care about. One is, how do we serve all the demand so that we want to match customers so that we can serve all the demand. And how to match the customers to cars so that utility is optimized for the system. Okay, so these are the questions we usually look at. We're interested in one additional question, that is, what if there is prediction? And the reason for this is because nowadays many of the systems like this, they typically have predictions about what's going to happen next, at least in a few time slots. In this example, you can sort of predict how many customers are going to come in the next few slots ahead of time, also how many cars there are going to come. So how do we incorporate prediction into algorithm design, and what the impacts of prediction is? These are things that we want to understand more. That's what we're looking for here. Now, more generally, actually, we have other systems or other scenarios that we also have features like this. The first example, I don't know if you can see, but this is Amazon. Amazon is already using prediction, trying to ship products to distribution centers that are closest to your house, so that whenever you place an order, they will get the delivery to your house very quickly. Also, in cloud computing, we can sort of predict the demand or requests for resources. Inventory control, we can sort of predict demand and supply for the different goods. Now, the common features they share are that, first of all, these are dynamical systems with service requirements, so we need to meet all these. And second, usually we are facing network components with coupled actions, so we need to jointly optimize them. And the third one is what I just mentioned. Prediction is now sort of widely available due to the sort of rapid development of big data and machine learning techniques. They might be imperfect, but they're there, so we're trying to make use of them. Okay. Now, if you take a look at the network control literature, so there have been a lot of great works. I think many of the MobiHoc attendees contributed a lot to this. But then if you look at the literature, we can sort of see that we don't usually look at the prediction learning and stochastic systems together. And we don't usually try to quantify how much error is going to impact the performance. And this is what we're trying to do here. So to make it precise, our objective are as follows. We're trying to develop a general prediction model, which hopefully can be used for algorithm design and analysis. We're trying to utilize prediction and learning and control, and we try to quantify the fundamental benefits and limits of them. Okay, so here's the idea. All right. So, of course, there are many challenges. So I outlined a few of them. I guess one is dynamic component. Well, usually we also don't have the statistics, and the prediction can be inaccurate, and we also need to deal with the interplay between learning and control. Okay, so these are the things we are trying to do. Now let me quickly summarize what our main contributions, and then I'll get into the model and the algorithm. So first of all, we propose a novel prediction model. It turns out to be general and it captures features of existing models. And we also designed a predictive learning aided control algorithm, which has nice properties, but the main idea is that you can sort of view it as a combination of receding horizon control as well as stationary control, depending on the system dynamics. I'll make that precise. And also we quantify the impact of prediction. What we're going to see is that prediction is useful in terms of reducing delay as well as accelerating convergence of the algorithms. All right, so let me present a general model, and then I'll use these to construct our algorithm. It's going to be quite abstract, but then I'll give you a simple example. Okay. So it's a time-slotted system. We use a network state S of t, which is sort of independent over time slots, and we assume that at each time, it has a distribution that's denoted by pi of t. Okay. For now, you can think of this network state as the aggregation of network conditions or mobility and so on and so forth. We also use I of k to denote the interval during which the case distribution takes place. Okay. So each distribution is going to last for some time, and then it will change to some other states. Now, what's different from previous model is that we assumed a prediction module, meaning that network operator actually gets access to a prediction window, and precisely gets access to this window of distribution prediction. And I'll tell you the conditions imposed on these distributions. Okay, but for now, it has the power to predict. Okay. Now, based on the network, the state, the operator is going to make some decision x of t, and you can think of that as being power allocation and routing decisions. And based on the state and the action, there will be certain system metrics that are generated. The first one is a cost, which we denote by f of t. It's a cost of, it's a function of the state and the action. And then action is also going to generate traffic into each of the queues. We denote that by aj of t. And also it's going to serve packets from each of the queues. We denote that by mu j of t. So this is how much you serve from each of the queues. And then our objective is as follows. We want to minimize the time average cost subject to queue stability. Okay, this is actually a quite general framework, and many of the problems we have seen can be formulated into this way. Now let me give you a very simple example to show you what we can actually do with this model. Now here we have a simple example. A base station is serving 4 users. There are 4 channels, so each one of them is denoted by CHI, so this is channel condition. You can think of that as fading coefficients. And then we have queues for each of the users, and AI denotes the arrival, meaning the number of packets getting into the queue for each of the user I. Now, and then we can sort of write that down as in terms of the general question. No, okay. Yeah. So the network state will just be these 8 variables, the channel conditions, and the arrivals. Now, the action you take is x of I for each I, meaning that whether or not you want to serve this customer. So xi being 1 means that you want to serve the customer, and it's 0 otherwise. And so the cost here we consider is the power consumption. So it's just going to be a function of the state as well as your control decision. So how many people you serve, you're going to consume certain power. And so the traffic in this case, since the arrival is sort of from the outside, so the traffic into each queue is just going to be a function of the network state itself. Now in the service, it's just going to be a general power rate curve that's going to be incurred as a function of your action. Okay, so from here you can sort of see that we're dealing with systems like this. You can also consider multi-hop systems, that's also fine. Now let me specify our prediction model. We call it the distribution accuracy curve-based model. So the idea is as follows. For these predictions that you can, for these distributions that you can predict, we assume that each one of them has a total variant distance to the actual distribution, which is bounded by this E of k. This is the error term. You can sort of think of it that way. And we assume that this E of k is known to the operator. Okay. So here's a pictorial illustration. So this is the true distribution, that this might be what you predicted. So this is the error curve. Okay. So you can predict anything that's predicted. Now a few remarks. Now this kind of prediction can actually often be done in practice. So you can use histograms, historical information, and also many companies are doing things like this. You can sort of predict the distributions more or less accurately. And also turns out that it captures nice features of existing prediction models. I'll not get into the details of it. And we are also going to make use of this average prediction error, which is really the sum of the errors that's incurred within this prediction window. Now, this is an indication of the prediction power you have, essentially. Okay. All right. So let me talk about our algorithm. Hopefully, I'm doing well in time. Now, the idea is as follows. The key idea is that we are going to try to control the system as well as to monitor the distribution at the same time. And what we are going to do is that if I'm seeing that the distribution somehow remains more or less stationary, then I'm just going to try to explore the stationary control, which I'll make precise. In a sense, you try to learn the distribution and make use of that, because hopefully you will get better performance out of there. Now, on the other hand, if I see that the distribution has been changing over time, then maybe I should not be using the history that I'm seeing. I should really throw that away and try to rely on the prediction, which is, it's basically the idea of receding horizon control. You try to make use of what you can predict, and you base that, you make your control actions. Okay, so here's the key idea. Now let me get into the detailed components. It has 3 components. So this is the network that's given, the prediction model that's given. So we have 3 components. The first one is a distribution change detector. The second one is a dual learning component, which I'll tell you what that is. And the third one is an online control, which is a queue-based control. Now, the distribution change direction, this is actually a key component. So I'm going to spend a little bit more time here. Hopefully, I can convey the idea. So what we are going to do is, conceptually, it's simple. So we're going to maintain 2 windows. Each window is going to contain some samples of the network state that we observed in the past. And then we're going to compare the statistics of the samples in these 2 windows. Basically, that's so these are notations I'll skip. And here's the idea. So we'll keep these 2 windows. This WD, I don't know if you can see it. Capital WD is the window that's going ahead of time. And WM is the window that's going to contain the remaining samples that we observed so far. Now, WD is also going to contain the predictions. Okay. And then we compute the sample distribution of empirical distribution of the samples we have in these 2 windows. What we do next is that we're going to compare the statistics. Now, first of all, if the WM window is not having a lot of samples, we do nothing. Because if you're not getting enough samples, there is no point in trusting the distribution that you're getting from there. Now, once you believe that you're getting enough samples, what we do is the following. First, we'll compare the empirical distributions in the 2 windows. If they don't match, then we'll say that something has happened, and we should throw away the old samples and try to adapt to the new distribution. Now, there is another rule that we impose, is that we set a time t of L. You can view that as a threshold. You use this threshold to determine whether or not you should trust that the system, the dynamic is sort of stationary or not. Okay. Now, if you have already accumulated these many samples, in addition to the second step, we're going to do another sort of check to see whether the distribution has changed. And the idea is that now I'm going to compare my empirical distribution with the predicted distribution, just to see whether or not this has violated the prediction. And as you can see here, this is the error term, and we also need to add a sort of additional fudge factor just to account for the randomness in the empirical distribution. And then if this happens, we will throw away all the packets, the samples that we observed in the past, and then we just move on to. Now I think I can give you a picture. So this is the original case, and if in the next time slot I do the comparison, nothing happens, I've moved this window ahead of time, and I'll enlarge this window. Now, if something wrong, if we see that there is something wrong, then what we'll do is that we'll throw away all the samples and we'll initiate the 2 windows at some point in the future. That's not going to affect the class. Okay. Now, once you do the comparison, we're also going to output the distributions. The idea is that if the system is very dynamic, meaning that the WM window is actually not growing very large, we keep saying that, well, you should throw away the samples. Then what we'll do is that we'll use this predicted distribution. Okay, we'll output that. And otherwise, if we see that this window can actually grow very large, in the case of stationary, it will. We use learning edit control, and in this case, we will output the empirical distribution for samples in that window. And then the next step is what we call dual learning. The idea is that we use the distribution we output from the previous step, and then we use that, we try to compute a Lagrange multiplier for this optimization problem. I don't have time to get into that, but you can sort of see that this is intuitively a formulation that can help us solve the control problem, but it's not quite. So we compute a Lagrange multiplier here, and then what we do is that we're going to use that multiplier and put it into a Q-based control. Now, for those of you who are familiar with the back pressure idea or the drift plus penalty, the approach, this is essentially that, except that when we're making decisions, we're not just using the actual Q size. We're using the actual Q size plus the multiplier we learn based on the prediction we get from the change detection module. And here's the intuition, but I guess I should probably skip the idea. Intuition is also, you want to use the multiplier somehow to replace a Q in decision making, so you don't have to accumulate a lot of packets. And you also need to subtract a little bit from that multiplier just to account for the error that you might be making in estimating that. All right, so a few remarks. It's an online algorithm. You can sort of likely use it for non-stationary networks as well. It requires zero prior information about the distribution, as I said. Okay, thank you. And here I also want to mention that detection really needs to be done carefully, because if this is not done carefully, you always think that the system dynamics has changed, and then you'll be operating at this transient phase most of the time. So this is actually critical. Now, I don't have time to get into the proofs, but I'll quickly tell you what we can get. First of all, it works well in the stationary setting. By that I mean you can actually get utility that's within order 1 over V of the optimum. So V is a parameter you can choose. And you can get a delay that's basically log V squared. So this is kind of nice. You need to drop some packets, but the dropping rate is small. Let me quickly say that the optimum trade-off is really the 1 over V and log V. So we are getting a log V factor away from that. Now the second case is non-stationary. In this case, if you choose the TL threshold to be something like this, I don't have time to get into it, but essentially it's EW to the minus 2. Then what we can show is that for any sort of interval where the distribution lasts for some time, you can get the utility to be very good, and you can get a Q size of this. This is a log V squared plus this term, which depends on the prediction error. Now, I just want to say that actually back pressure, if you run the back pressure algorithm, it takes a longer time to get a similar performance. Now, I also want to emphasize that we can sort of see here that this is the error term. It comes into the queuing part. So prediction accuracy actually impacts the Q size. Okay. Now let me quickly also go over this. Well, in the case of perfect prediction, we can get even nicer results, but let me sort of skip that. I also want to talk about convergence. That is the time it takes for a Q to get to within a distance of the optimum multiplier that you want it to get to. Now for this, we can actually prove the following results. If there is no error in prediction, you can get logarithmic the time for convergence. If there is error, then we have two results. The first result is that you can get to a very small neighborhood for using this amount of time, and you can get to a larger neighborhood in, again, a logarithmic time. Now, I don't have time to go through the details again, but I can sort of tell you that the convergence is faster than existing results. And I also want to highlight here that we again see this prediction error term here that's appearing in the convergence. So basically it says a prediction helps convergence, even if it's sort of imperfect. Now, quick simulation results, and then I should be done. A simple 2Q network. And we are getting, so this one is the average power performance and the average Q size. So this is, blue is back pressure, and the other two is the predictive learning ones, with and without error. We can see that in terms of power, we are doing okay. So here the objective is to minimize the power. So in terms of power, we are doing the good. In terms of Q size, the learning approaches are doing much better compared to the common back pressure algorithm. Now this is the one that's more interesting. We are looking at the convergence of the Q size to its steady state value. Now the blue one is back pressure. We see that it takes longer time to converge. The red and green are the learning-based approach. We see that they're converging faster. So we change the distribution in the middle of the simulation. But you can sort of see that. Thank you. I will be done in 30 seconds. we can sort of see that after you change that, they again adapt quickly compared to backfish. Okay, so it's kind of rushed, but let me summarize anyway. So we propose a novel prediction model. It turns out to be general and helps with the analysis. We developed this predictive learning aided control, which has many nice properties. I will not go through them because of time. But the main takeaway message is that prediction is actually useful. It helps reduce latency and it accelerates convergence. So I guess with that I'll stop. Thank you very much.